Hi everyone! I want to go over Gauss's law as a means of calculating electric fields in this video. It's going to be a repetition of what we went through in the lecture. You can also follow this from lecture notes and printable lecture notes and additional contents in my folder. So let's go over it and see real quick how we were using Gauss's law as a means of calculating electric fields. And then we're going to try to finish up all the material that's left in the lecture notes that we couldn't cover in the lecture or makeup lecture. So guys, Gauss's law is an equation. It tells you what total flux through a surface is, and it does that without even calculation. So flux by definition is number of electric field lines passing through a surface. Right? So here we have an electric field. If you multiply it by the area that you have times the cosine of the angle between the surface area and the E field, area is a vector by the way, then you get the total number of electric field lines passing through that surface. If you have a closed surface, E dot dA integration gives you the charge that is inside the surface divided by epsilon 0. And if you have a surface with no charge inside, the total flux through will be 0. That means that all of the electric field lines that go into the surface, they come out. All right? They don't vanish in the inside. So you get a 0 integral for a closed surface with no charge inside. But if there is a source of electric field inside that Gaussian surface, the surface of consideration, then the total flux is proportional to the charge that is inside the surface, and there's a proportional to constant 1 over epsilon 0, the electrical permittivity of air. All right, so this Gauss's law is a flux calculation. We can use this, is what we're arguing in this course, that we can use this equation to actually pull out the E in the equation and have some sort of an expression where we can say, hey, E is equal to Q1 over epsilon 0 times area. That's what we're going to try to get at. So we want to use Gauss's law to calculate electric fields, and for us to say E is equal to that, E has to be out of this integration, first of all. So we actually have to choose a surface, an imaginary surface, that will help us give us that beautiful flux calculation where E is uniform on the surface, can come out of the integral, and the area between E and A is predictable, 0, 90 degrees, some fixed value. So it can also come out of the integration, and we're going to have this flux expression not as E dot dA integral, but as E times A times cosine fixed number. All right, so for us to be able to do that, we need to choose a Gaussian surface around our charge, and we need to choose one specific surface that can give us that freedom to get rid of integration. So let's see this on an example. Here is an infinitely long line charge. We're going to get to this problem. We're going to try to calculate electric field of an infinitely long line charge at a distance d from the line charge using Gauss's law. But I want to go over a few details we should watch while trying to use Gauss's law to solve for this. First of all, guys, you need to kind of know what you expect from electric field lines or how you expect them to be. So you kind of have to have a three-dimensional picture in your brain of the electric field lines of that source of charge. All right, so here the line charge creates an electric field that opens up radially in all directions at its cross section, and then it keeps going the same way on the axis of the line charge. All right, so you have these E field lines opening up in all sorts of directions directly away from the line. They're all perpendicular to the line, these vectors, and the vectors repeat themselves as you go along the line. So this is the picture we have for a line charge. To be able to solve for the electric field of this line charge, we need to, okay, 1, draw the electric field lines. 2, we need to define, pick, draw an imaginary surface around this charge. We're going to call that our Gaussian surface, like a cube, a cylinder, a sphere. Actually, most of the time, including maybe the rectangular prism, these are the surfaces that we're going to be picking from. But only one surface most of the time works for that particular charge. How do we know? Well, the E field lines could be estimated on that surface. Like let's say you pick a surface the same distance from the charge, then you know that the E field lines on that surface will be uniform. They will be the same number. So you want to pick a surface that can give you that, because E has to come out of this integration. Also, we said that the angle has to be predictable. So this means that the surface of your picking should have E field lines sweeping the surface. Sweeping the surface means what? If I draw E field lines on this plane of the board right now, okay, or the screen. If I draw all sorts of vectors on the plane of this screen, the area of the screen is perpendicular to the screen, so it's towards you guys, right? Any vector on the screen is going to be perpendicular to the area vector because they're on the plane of the screen, okay? That means that these vectors that I draw on this plane are sweeping the surface. They're on the surface. They're perpendicular to the area vector. So if I was to calculate flux through the surface with E fields on the plane of the surface, then E dot dA is 0. Okay, so it's predictable, it's 0. But a flux equals 0 is not going to help us solve an electric field, but we can use it maybe on some part of our surface. So if we have a cube, if we have a cylinder, they have multiple surfaces to work with. So maybe we can have that on some parts of our closed surface. On the other parts of the surface, we would want to have an E field that is perpendicular to the surface, meaning E field being parallel to the surface area, the area vector. Okay, so we have an E times dA times cosine 0 here. So that's the criteria we're going to use to pick our Gaussian surfaces. Once we do that, we can calculate the flux on that surface without having to integrate anything. And then we define a Q in this Gauss's law expression using definitions of charge distribution, or if you have a single charge, just put everything in there. Then you place everything in the Gauss's law equation and calculate a final E field vector or number, magnitude. So that's how it's going to work out. Before I go into the line charge, let's do a simpler one, which is the a point charge. We already know what the E field is going to be, KQ over R squared. We have introduced this in class, right? So let's try to find this E using Gauss's law. All right, so it's like a derivation. First, we need to define a surface so on which the E field lines can be estimated. All right, and they have to be uniform on some or all parts of the surface, okay? And on the other parts, if it has multiple surfaces, the electric field lines should sweep the surface so we can get a 0 flux on that particular surface, okay? Then we also, our other criteria is then including some or all of the charge in this Gaussian surface, so we don't have 0 on the other side of the equation, basically. So here is our point charge. What do? Well, first we imagine the E field lines, we said, right? So E field lines of a point charge are radially outward in all directions in 3 dimensions. We can select multiple surfaces around this charge, enclosing this charge, okay? It has to include the charge. It can be a cube, for example, centered at the charge, a sphere centered at the charge, a cylinder centered at the charge, around the charge. Only one of these surfaces is going to give us a very easy flux calculation. Let's say you're in the exam and you didn't know which surface to pick around your charge. Just pick a random one. And you're going to see that while trying to calculate the flux, if you're stuck in this integration, if you cannot write a specific angle for between E and dA, then you will know that that's the wrong surface anyway. Then you'll go back to the question and change your surface. Try to find a different one. So let's say we drew a cube first. There is a cube around our charge. Wonderful. Okay. So let's look at this one of the surfaces of the cube. Let's take the side one. Though same thing is going to hold for all surfaces of this cube. But let's look at the side cube. All right. So we have the E field lines. Let me have all my wording in there. So we have these E field lines. All right. That are going in all sorts of going through the sheet, not the sheet, through this surface of the cube in all sorts of directions, okay? We have a certain area vector for this surface, for the side surface of the cube. It's towards the right. So all of our dAs are towards the right. But the E fields, since they're radially outward from the charge, they have all sorts of directions. Can you here write a constant angle between E and dA? Absolutely not. 0 degrees at the center line of the cube, but gets bigger and bigger towards the edges of the cube here. So no constant angle. Plus, E field may not be uniform on the surface. Why? Because all points on the surface are different distances to the charge. Here is the side surface. The center is closer to the charge source of our E fields. And these points, for example, on the cube, they're further away from the charge. So no constant E, not uniform. Cube is not a good choice, you guys. Let's look at the cylinder. Well, same thing goes. Let's take this base of the cylinder, the circle here, the base. All right, same thing goes. You have E field lines at all sorts of angles to the surface, but where's my dA? There it is. All right, and you have one fixed dA vector towards the right. So there is a variable angle here, not a constant angle. Plus, since all these points have different distances to the charge, E field is not the same number everywhere. So not a good choice again. So what is that one surface that will give us the same E field around this charge? Well, if E field is going to be the same at a fixed distance from the charge, then E field, let's say, at 1 centimeter from the charge is the same as this 1 centimeter from the charge, is the same as this 1 centimeter from the charge. So what is that one shape that will give us that? The same distance to the charge. Well, it's the sphere, right? It's a sphere centered at the charge. So it can give us the constant distance to the charge. So my E fields on the surface can be the same number, meaning uniform. Okay, if we take a sphere as our Gaussian surface, the area vectors on the sphere, the little dAs, I cannot talk about a single area vector like towards the right, towards the left. No. For a sphere, I have many area vectors. So I have to select a little region on the sphere. And the area vector is towards the out of the surface. It has to be perpendicular to the little surface that I'm picking. So its obvious direction is radially outward, dA. Radially outward. Well, the E field created by the positive charge is also radially outward, right? So my E field is parallel to my dA. Would the situation be different if I selected another point on the sphere? Let's say a little towards you guys. Well, dA would still be radially outward, and E field created by a positive charge is still radially outward. All right, so again, my E field will be parallel to my dA at that particular point. So wherever I am on the surface, E is always perpendicular to the surface, which means E is always parallel to dA. All right, also, all these points on the sphere are the same distance to the charge. So E1, E2, whichever E I pick on the sphere's surface, it will be the same number because it's the same distance to the charge. So E field is uniform on the surface. So definitely sphere centered at the charge is a good choice. Wonderful. All right, so let's do the math then. So this is what we do. We draw a Gaussian sphere around our charge. And on that sphere, E dot dA equals Q in over epsilon 0. And guys, when you're doing Gauss's law, this expression is only valid on a surface, on a Gaussian surface, the imaginary surface that you are going to be drawing. So solution without a surface doesn't make sense, hence in the exam it's going to be 0 points. Okay, so make sure when you start solving, even though maybe you know that you're working on a sphere, you have to draw it and show it on the paper, otherwise it's not going to be graded. All right, so I go draw my Gaussian surface, I write Gauss's law, and Gauss's law will tell me what to do next. It tells me that I need to calculate flux. Okay, let me calculate flux. E dot dA. Well, E is parallel to dA is what I argued. Wonderful. So the angle in between is cosine 0. So the dot product reduces down to E times dA times cosine of 0, which is charge inside over epsilon 0. That's Gauss's law. We're going to get to Q in later. Since E's are the same distance from the charge, E is constant in this integration. It can come out of the integration, reducing our flux calculation to E times area of the sphere. So this is just E times A. Integral of dA is A, right? So that's the area of the sphere. Equals Q in over epsilon 0. Wonderful. So E times area of the sphere equals E times 4 pi r squared, right? That's the area of my sphere with radius big R. That's what I picked. You can call it a small r or anything. That's the radius of my Gaussian sphere. So that's the area of my Gaussian sphere equals Q in over epsilon 0. Qn is the charge inside the Gaussian surface. Here is my Gaussian surface. All of my charge is in there. Let's call it small q. Sorry. So E times 4 pi r squared is Q over epsilon 0. Hence E is Q over 4 pi epsilon 0 r squared. Wonderful. And since 1 over 4 pi epsilon 0 is K, we just rederived KQ over r squared for an electric field of a point charge. Wonderful. Let's move on to the line charge. All right, so what's the electric field at a distance d from the line charge, the infinite line charge? Let's follow the same steps. Draw the E field lines and then define a Gaussian surface according to these E field lines. So here are our E field lines. They're opening in all sorts of directions in 3 dimensions, radially outward. And it's like the polar coordinates, this E field line orientation. So from the side, this is what my side view looks like. Let me have all my animation there. So this is a side view, line charge coming towards us. E field lines are opening up in radial directions at this cross section. So this is the side view. I have to define or pick one of these surfaces around my line charge, okay? So that E field lines on it can be uniform. E field lines sweep one of the surfaces of these shapes, right? Or E field lines being perpendicular to the area, meaning parallel to the area vectors on some or all of these shapes. Okay, so which works best? Well, I can immediately eliminate some, right? Like, for example, the sphere, guys. Still, we're going to look at the sphere, but on the sphere, if I enclose my line charge in a sphere, by the way, important note that I'm not enclosing all of the line charge. Since it's an infinitely long line charge, I cannot enclose all of it in my Gaussian surface. So what do? I enclose some of it. So here is the part of the line that is in my Gaussian rectangular prism, part of the line that is inside my Gaussian sphere, Gaussian cylinder, another Gaussian cylinder put sideways. Okay, so I'm enclosing some of it. So let me see if any one of these gives me 1, a uniform E, 2, a predictable angle. So here, for example, the sphere, if my line charge passes through a sphere, these points on the sphere are closer to my line charge, hence bigger E field. These points on the sphere, they are far from my line charge, so they have smaller E fields, no uniform E field on this shape. So I'm going to eliminate sphere right away, but I'm still going to get to it though. All right, I'm left with 1, 2, 3. So these two kind of look similar. I can look at their top surfaces and make a judgment. Okay, let's do that. So let's put a rectangular prism enclosing some of our line charge. And let's look at one of these surfaces on this rectangular prism. Let's say the top surface. On the top surface, okay, my E field lines, how are they? See, at the center of this rectangular surface, the E field lines are straight up. But as you move a little towards the sides, then the E field lines start bending. They will change their angle. Hence, on the top surface, you cannot talk about a fixed angle between E and dA. Right? So all different angles on the top surface. Also, see, this is a surface straight above the line. The center of this surface is closest to the line. As you go away from the center of this surface, you are farther away from the line, meaning no uniform E fields. Hence, rectangular prism is not a good choice. Also, guys, if I put a cylinder this way, see, the top surface is going to have the same problem as this top surface, so this is no good either. I'm left with one choice, a cylinder put sideways, but let's see if that works. Okay, let me see if it works. Well, here the E field lines, look at on the circular surface, the E field lines. They are on the plane of the circle. The area vector is towards the left, right? Perpendicular to the circle, and all of the E field vectors are on this circle. So the E field line sweeps the circle, which I'm going to call the base of the cylinder. So they sweep the base of the cylinder. Okay. Let's see the round side. So here my flux will be 0 anyway. Let me see the round side. Looking from the side of this line. So the line charge is coming towards us. And the E field lines looking from the side, they are radial in direction. And this is what the cylinder looks like. So this black region is the round side of my cylinder. Okay, on this round side of the cylinder, my E field lines are coming towards the surface. Towards the surface, right? I'm going to show you that with better animation. Also, all of these points on the round side are the same distance to the charge, a radius distance. So E field is uniform on the round side. So definitely cylinder is a good choice for me. Let's just remember another reason why we would eliminate the sphere. If I take here's a sphere, and if I take the cross-sectional view of this sphere, the cross-section looks like a circle, right? Let me take the plane of the screen, and just look at that. So on the plane of the screen, E fields are either pointing up or down. Little dAs are radial in direction. So here, if I pick this location, E and dA may look parallel, but if I move slightly across the side surface, let's say here, area vector is radially outward, but E field is still up. Closer to the center of the sphere, area vector comes flattened, E field is still up, so there's a variable angle here. It's not going to work in my flux calculation, so that's why sphere is not a good choice. Reason number 2, basically. All right, wonderful. So this means that we have to pick a cylinder as our Gaussian surface around our line charge. This is an image I found off the internet. So here is a line charge, for example, if we take a cylinder like this around our line charge to calculate our E field using Gauss's law, see the E field lines are coming perpendicular to the surface on this round side. They're perpendicular to the surface on this round side, which makes my calculation very easy. So let's go into the calculation. I'm given a line charge. Now I know that cylinder is a good choice. I draw a cylinder around my line charge. Its axis has to be aligned with my line charge, okay? And my flux calculation on this cylinder includes 3 terms because the cylinder has 3 surfaces. Let me call them subsurfaces. So one is a circle on the base, call it base 1. One is another circle here, call it base 2, and this round side. So 1, 2, 3 flux calculations is what I need. On the bases, I don't even need to calculate anything for the reasons we argued earlier. The E field lines are on the plane of the circle. Area vector is perpendicular to the surface of the circle. Hence, all of these E fields on the surface, they are perpendicular to the area vector. Hence, that gives me, in my flux calculation, a cosine 90 degrees, right? E times dA times cosine 90, which is 0. So the flux on the bases, both of them, is 0. Okay? That makes sense. So all I need to do is calculate the flux on the round side. Let's look at that. So the side surface from the side view looks like this. If I pick a little area here, a dA1, right, on the top of the cylinder here, the E field will be up and area vector will be radially out, looking from the side. This is my little dA. That's what the vectors look like. They're parallel, right? E1 is parallel to dA1. Let me move on to a different side here, for example, right? E field is radially out and away from the line charge. Let's look at it from the side view. This is the little area that I picked. The dA vector is radially out, perpendicular to the surface. E field is also radially out, so they are parallel again. If I pick a third surface, let's say here, again, looking from the side, the dA is radially out, and the electric field vector here is also radially out, so they are aligned. So any dA that I pick will be parallel to my E field, which works for me because it gives me a constant angle in my flux calculation. Also, all of these points on the surface of the round side, right, they are the same distance to my charge, so these E field values are the same number. So hence, E field is uniform in my flux calculation. It can come out of the integral. Also, I have a 0-degree angle in between, so I have E times cosine 0 times dA, which is E times dA, and E is uniform on the surface, comes out of the integration, leaving me E times area of the round side. So E dot dA reduced to E times A. A being area of the round side. Alright, so let's talk about dimensions. I wanted to know the electric field at a distance d from the line. So my Gaussian cylinder has to have this radius d. So I'm d distance away from the line charge at all times. But the length of this Gaussian surface, guys, it doesn't matter. Let's call it a random number h. Call it L, whatever you want to call it. So the length of my Gaussian surface is going to be small number, smaller than the length of the line, and it can be a random number. So h is my random number. Okay, so how can I calculate the area of this round side? 2 pi d times h. That's it. Wonderful. So this part of the equation is then set. Flux equals q in over epsilon 0. My total flux is 0 on the basis, 2 pi dh times E on the side. Hence, that's my total flux, 2 pi dh times E field that I'm looking for. Wonderful. So 2 pi dhe equals q in over epsilon 0. Great. What is Q in? It's the charge in my Gaussian surface. So looking in a transparent picture like this one, here is the charge that is inside my cylinder. The charge that my cylinder encloses. Okay, Q in. Okay. So how can I calculate it? Well, I have a charge distribution lambda and I can use its definition. By definition, lambda is Q over L. So if I want to find a Q in, all I need to do is multiply lambda by the length that I'm interested in. So there we go. Then Q in is lambda times H, which is the length of my Gaussian cylinder. I'm enclosing only H length of this whole line charge. Wonderful. Let's plug that in. So 2 pi dHe equals lambda H over epsilon 0. There we go. We can pull the E out of this equation, which gives us lambda over 2 pi d epsilon 0 for our electric field. Replacing 1 over 4 pi epsilon 0 with k, 2k lambda over d. Same result you would find using the integration method, right? 2k lambda over d. That's the E field at a distance d away from the line charge, period. Wonderful.